We've seen several examples now where we could use initial conditions to highlight or have our solution only reflect one part of the two solutions that we get in a 2x2 system. That was for real solutions though, real eigenvalues, real eigenvectors. Here we're looking at a case where we get complex eigenvalues and eigenvectors. Can we still use this initial condition strategy to pick out one of the two solutions? Well, remember what the general solution looks like for this complex value case. We end up with e to the 3t times the cos of the coefficient in here, so cos of 1t in this case, and then we multiply that by, if you like, this vector here, the 1, 2 vector, which is the real component of this thing here, and then we subtract sine of t, so the same frequency, but then we use the everything without the i's for the remaining part, 1, negative 1, for this side. And we should include a constant in front of that. We get c1 times this complicated solution here, and then c2 e to the 3t. What we do is keep the cos and swap the vectors. And we flip the sign, so a couple of rearrangements, but nothing too serious for the second solution. Just to summarize, we swap vectors and we make the sign multiplier coefficient positive for the second one. And just a reminder, we don't need to look at the second solution. It's basically the same as the first, or it's tightly related to the first. And this construction here was based on both of these together. So what about our initial conditions? Fortunately, at t equals 0, this complicated mess does get simpler because sine of 0 is 0, and e to the 0 and cos of 0 are both 1. So we get a little bit of simplification there. In this particular case, we'll have c1 times 1, 2. No, that's not bad at all. Plus c2 times the cosine 1, negative 1. So in some sense, we get the same simple construction that we got in real eigenvalues and eigenvectors. We just get there through a slightly messier preamble. So the shorter answer is, can we use initial conditions to select one of the solution behaviors? Yes. If we picked x of 0 equal to a multiple of, say, the 1, 2 vector, then we'd get x of t equals just the e to the 3t blah, 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 c1 part, with 0 for c2. Now, what's a more interesting follow-up question is not, can we do this isolation of solutions, but does it matter if we do or not? Because if you look at what we get with c2, we have a cos and a sine as well. So the issue isn't so much that we can't isolate one solution. The issue is that both solutions look pretty similar or behave very similarly. If we had this solution, I said, oh, you're going to have an e to the 3t plus a cos times this vector and a sine times this vector, and then I gave your colleague this solution and you said draw them or sketch them, you would get pretty similar looking things. In fact, that's where we're going to go next, is to look at these kinds of solutions. On the plane x1, x2, thinking of the kinds of solutions we get, we'd have cos of t's and sine of t's and vectors that go with that. What we'd get is vectors out that are eigenvectors, but at the end of the day, these represent rotations in the x1, x2 plane. If you think of the classic example of cos t and sine t as a vector, that gives you a perfect circle. If you start off with axes and go cos t, sine t are my points, then you end up going infinitely around in a unit circle. So when we see the same kind of thing here, but we have this positive exponential, which increases as t increases, that's the amplitude of the circle. So let's be more specific here. Amplitude or radius. What we get with these kinds of solutions are curves that start somewhere and they don't go in a circle. By the time they get back to where they started, they've spiraled outwards. We've scaled that initial vector by some exponential here, and then it would keep growing out from there. If we started a solution in towards the middle, it would have the same kind of behavior. And if we start even closer to the middle, it'll still start small and then spiral out and out and out and out, because we had this cosine driving the circular behavior, and we had the exponential growing the radius or the amplitudes. Sometimes this is called an outward spiral form. Doesn't matter which solution you get, C1 or C2, you're going to have this basic shape. It should not come as a huge surprise that if we have a negative real value combined with, in this case here, a cos 2t and sine 2t, if we started here, we would get circles. And again, the directionality depends on the details of the eigenvectors. We'll draw this one going in clockwise, and this would be called an inward spiral for exactly the same reasons. As time goes on, we're using a smaller and smaller multiple of this cos and sine, and so we end up heading towards the origin in the long run. And if we started somewhere else out here, say, we would end up following inside that other spiral somehow. Again, heading inwards over time. With these outward and inward spirals in mind, it also is worth seeing what happens at the transition point. Well, where's that transition? It's about the real coefficient here. Any positive coefficient leads to exponential growth, or outward spirals. Any negative value leads to inward spirals. On the next page, we'll see the zero value. If we had a 0 here, we would simply have e to the 0t, well, that's just better known as 1, times our cos, in this case here, of 2t, sine of 2t combinations, and that would be a constant radius amplitude, whatever we're imagining it, 1 dimension or 2 dimensions. And so that would be something like this. Wherever we start, we're going to be on some oval or circle, but it turns out we're going to have a very simple pattern, and once we start at one point, we're going to return to that point, as we can see with the functions here. The cos and sine will eventually repeat themselves, and we'll end up back at our starting value after one period, and after 2 periods, and so on. When we look at the relationship between initial conditions and simple solutions, what we can do is choose the initial conditions as a multiple of one of the eigenvectors. If we do that, then our solution is only going to reflect or only going to include multiples of that eigenvector. That's only interesting, though, when eigenvalues are real. That's when we really see the distinctions. With complex eigenvalues, they look pretty much the same. We're talking a sine and a cos either way with the same exponential both ways. So we don't usually care that much, quite frankly. We might care about the exponential, whether it's e to the positive value of t or e to a negative value of t, but that's not really about one particular part of the solution or one eigenvector. Where it does get interesting is when we go to 4 or more variables. Let's say you had e to the 4t and a cos 2t sine 2t versus an alternative, which would be, e to the negative 2t cos of 3t sine of 3t. There, if you could elicit this behavior by choosing the initial conditions, you would get an inward spiral. In 4 variables, though, so it's a little more complicated already. Whereas this one, if we could choose the initial conditions to match this, we would end up with an outward spiral. And every other solution is a combination of those two. So there, with 4 variables giving us lots more room for maneuvering, we can get much more interesting behaviors. We'll see that going forward.